Before I go any further in the videos on talking about antennas, I do feel like we need to stop and make some qualifications about the discussion that we're having. And that is that there are distinct differences in the radiation from an antenna that can be observed as the distance away from the antenna becomes larger and larger. So we have three distinct regions of operation for an antenna. In the reactive near field region, which is this dark gray in the image, the reactive field predominates dominates. In this region, any antenna will inductively couple to the source antenna. So if I were to insert another antenna here, these antennas do not connect to one another via radiation. Instead, they connect to one another via inductive coupling, just like a transformer. The distance of the reactive region is given by 0.62 times root D. So that's R1 there, where D here is the largest dimension of the antenna. And of course, actually, yeah, so root D is just the largest dimension of the antenna, the root of the largest dimension of the antenna. Then as we leave the reactive and near field region, we get into what's called the radiating near field region, also called the Fresnel region. And in here, the angular field distribution is dependent upon the distance from the antenna. So the density and distribution of the E field and the H field is dependent on distance away from the antenna. And that's because we can't consider radiation in this portion as a plane wave yet. So basically what we're saying is in this portion of the radiative field, our plane wave approximations don't work. In the far field region, which is the distance beyond this light gray circle, the angular field distribution is independent of the distance from the antenna, and this is called the Fraunhofer region, and this is where the plane wave approximation takes over. And that distance is 2 times the largest dimension of the antenna squared divided by lambda, where lambda is just the wavelength of whatever the driving signal attached to the antenna is. It's the wavelength there. So what does this mean for us? Why am I pointing this out? So if we are to observe the amplitude pattern shape of an antenna in the different fields, the shape is going to change because of the variations in the E field, whether we're in the reactive, the Fresnel, or the Fraunhofer range. In both magnitude and phase, I mean, they're going to change. So in the reactive near field region, the pattern is more spread out and it's almost uniform, as we can see here. As we move into the Fresnel region, the pattern begins to smooth and form lobes, like we showed in our antenna patterns. In the Fraunhofer region, the pattern is well formed. It consists of the previously described major lobes and all these minor lobes. And from this analysis, we can see that the antenna, as we think of them, they must operate in this Fraunhofer far field region, meaning that two identical antennas to communicate with one another using radiative communications must be separated by a minimum distance of 2d squared divided by lambda, where lambda is, or d is basically the largest dimension of the antenna, the radiative dimension of the antenna. And so we have to be in this far field condition, which is the plane wave condition that you're used to.